Okay, 2.2 is called slope fields, and there's a very good possibility you've already seen a bit of this in AB. So perhaps that would mean you remember that a slope field is a graphical representation of the slope of a function at various points in the plane. A slope field is a graphical representation of the slope of a function at all kinds of different spots, points in the plane. And let's just get the examples going here, shall we? Given that dy dx equals x, so the derivative equals x, sketch the slope field of the function. So what would be the slope field of dy dx equals x? So it's like we're sketching the original function. You know what I mean? But remember that, I guess one of the big ideas here, that it was one of the big ideas last semester, the derivative is slope. So this is basically saying that slope equals x. So as I'm saying, it's written right here. To do this, we notice that the equation is essentially saying that the slope of the curve at any point is simply the x value or x coordinate of that point. It's like literally saying that slope equals x. Okay, so whatever the x coordinate is, like this point has an x coordinate of 1. So the slope, that means the slope at this point is going to be 1. So this is a pretty good little line segment that has a slope of 1, like 1 over 1. But this point right here also has an x coordinate of 1, and so the slope here is also going to be 1. It's again, whatever the x coordinate is, I guess that's what the slope is equal to. So all these points, dy dx equals 1, because x is 1. And so this would be, so all of these points where the x coordinate is 2, dy dx would equal 2. So here's, little line segment that has a slope of 2. And so we're kind of like drawing these little line segments. And likewise here, the slope would be 3 because the x coordinate is 3, x coordinate is 3, so dy dx is 3. And so these are a little bit steeper, like a slope of 3 is steeper than a slope of 2 or a slope of 1. So here's all little line segments for those spots. Now, at this point, the x coordinate is 0, so that's going to be so that's a slope of 0. Sorry, right there. That's a slope of 0. Just like all these other points are going to have a slope, dy dx, equal to 0, because that's just what the x coordinate is. And then all of these points have a slope of -1. And so all these line segments are roughly or exactly, I can't remember if I measured these out exactly with using clever tricks, but that would be something representing a slope of -1, and right here I'm using this to represent, actually, wait a second, no, that's even steeper. You go there, buddy. This one's not as steep. This one would be the slope of -2. Remember, negative slopes go downhill and positive slopes go uphill. Can't believe I'm doing all this in live time. Do 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 do. I'm almost done. Okay, so there's the slope field. Just doing like one point at a time based on what the equation says. dy dx just equals x, whatever x is. This example would be easy to compare to the actual graph or graphs, of the general solution. All right. If you think about last section 2.1, actually solving this and getting the general solution, moving dx over here and integrating both sides and coming up with a general solution, you would get y equals x squared over 2, but it's a general solution, so plus c. And so that is what this is what y would equal, right, as a general solution. So this right here is a pretty decent graph of y equals basically 1/2 x squared. And why don't I also do this, calling an audible. So these are just some of the particular solutions for different c values. And these are just all like kind of the nice integer c values. Like, c value doesn't have to be an integer. There could be a graph here, a graph there, a graph there, a graph here. You know what I mean? It doesn't really matter, but as you can see, like now compare all of these different particular solutions with different c values to the slope field. I mean, isn't it kind of looking like it's kind of matching up a little bit? Because these are just like all the slopes at different spots for different solutions, well, this next one is going to be kind of repetitive. I mean, look at this next example. Given that dy dx, or slope, equals y, sketch the slope field. Well, it shouldn't be all that difficult considering what we just did. It seems like now your slope is just going to be whatever the y coordinate is at whatever point. So let's say you went to this point right here. The y coordinate here is -2. So your slope segment, is going to be, the segment's going to have a slope of -2. Well, everywhere on, I guess now we're going to kind of group points like this. So all of these points have a y coordinate of 0. So the slope segments are going to be 0. So that's all of those. Again, I can't believe we're doing this in live time. Oh well. And all the y coordinates here are +1. So this is roughly a little line segment of +1, up 1 over 1. 1 over 1. And all of these points have a y value of 2, and so yeah, I guess this one, eh? And so all these little line segments have a slope of 2, you know, 2 or 2 over 1, up 2 over 1. And then all of these points are going to be a little bit steeper because the slope of all these little segments would be 3, or 3 over 1. Of course, these would all be exactly -1. These would all be -2 because all these y coordinates are -2. And -3. -3 over 1. Remember, positive slopes go uphill. Negative slopes go downhill. FYI, the graph of the general solution, at least for c equals 0, well, that doesn't make any sense. The particular solution is y equals e to the x. You know, so actually this is more like a particular solution when c equals 0. And e to the 0 equals 1. E to the 1 equals about 2.72. So we're just going to graph this one particular solution. And your graphing calculators could help out a lot right here. I guess we're just making a little numerical table. Okay. So these are all the, this is the slope field. So what does this graph look like? Let's go to blue. Alright, so when we plug in 0, we get 1, so there's a point. When we plug in 1, we get about 2.72, so there-ish. When we plug in 2, we get, whoa, 1, 2, 3, 4, 5, 6, 7, like somewhere up here, man. And if we plug in -1, we get about 0.37. If we plug in -2, we get about 0.14. You know what I mean? So this graph, e to the x, it's a typical like exponential looking, oh gosh, just using my mouse, oh god, I don't like that. You know what I mean? I'll just kind of move the pen through it. So that's the graph, you know, and it's going to ride along the x-axis. So as you can see, I mean, look at this slope field, you know what I mean? Basically, we know that our graph right here, where c equals 0, is passing through the point 0, 1. So right here, we know that the c equals 0 solution is going to pass through this exact slope field and you know, kind of go like this, right? So this red line segment at least fits this particular graph, but remember the slope field is containing all kinds of particular solutions with all kinds of different c values. You know what I mean? And let's do, I guess, one more example. Yep, last example. Construct a slope field for the differential equation dy dx, which is slope, equals the cosine of x. Interesting. And look at how the x-axis is labeled here with like pi, and so this must be pi over 2. This must be 3 pi over 2. Anyway, this differential equation, or diffie-q for slang, how the cool kids say differential equation. So this diffie-q is basically saying that the slope is always the cosine of the x-coordinate. So wherever we're at, whatever point we're at, it looks like the slope there is just going to be the cosine of whatever x is. Okay? So all of these points where the x-coordinate is always negative 2 pi, looks like that's going to be 1. That was a little premature. Here we go, baby. The biggest one yet in live time. Oh my gosh. Let me guess. You are strongly considering fast forwarding through the video if that hasn't occurred to you already. But so before you do that, just obviously all these coordinates, x equals negative 3 pi over 2, and the cosine of negative 3 pi over 2 is 0. And all of these points, cosine of negative pi would be negative 1, and all of these points, well, right here, where was I pointing? So all these points, cosine of negative pi over 2 is 0, and all of these points where x equals 0, the cosine of 0 is going to be 1. And if we went on to like the cosine of pi over 2, that should be 0. The cosine of pi should be negative 1. 3 pi over 2 should be back to 0. And the cosine of 2 pi should be positive 1. So basically, now is the spot where you might want to fast forward through all of this, because I might be here for another couple of minutes. Or you might as well just let the video go and copy all this along with me. We're in this together. 0. So cosine of negative 3 pi over 2 is 0. Come on. You can probably write these down on paper a little bit faster than I can. What else was 0? The cosine of here, right? I just realized that the cosine of 0 is also 1, so I'm gonna have more uses for these guys, because the cosine of 0, when x equals 0, the cosine of x is also equal to 1. Now what? Cosine of negative pi? Well, that's going to be the same as pi. That's going to be negative 1, is that right? Cosine, what it says over here, cosine of negative pi is negative 1. That should also be for pi over here. Oh my gosh. This is easy, but so arduous. We're getting there. Alright, so the cosine of wait a darn second. 2 pi So, wait a minute. The cosine of pi is -1. Yeah, there's more zeros, right? So sorry, I feel like I need to double check this in my head. So cosine of 0 would be 1, positive 1, and then at pi over 2 it'd be 0, huh? Cosine of, so this is like 90 degrees, and then now we're at -1, so it goes positive 1, 0, -1, 0, and then back to positive 1. And so going in the opposite direction at -90 degrees it'd be 0, and then -1, and then back to 0, and then, okay. Yep, we're good. For some reason I let these extra line segments down here confuse me for like a split second in a weird way. Come on, buddy. Come on, buddy. Oh my goodness. Let's get these out of here. Holy moly, what a slope field, man. By the way, as I let slip a little bit, seems like forever ago now, by the way, the general solution is y equals the sine of x plus c, right? So all of these little line segments represent a lot of different plus c particular solutions of, but y equals the sine of x plus c. Now, if our c value was 0, right, I think, like let's say our c value was 0, we would have a particular graph that goes through there. Wouldn't it also exactly go through here? And it would exactly go through there, and it would exactly go through there, and it would exactly go through there. Also, here, 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 and here. That doesn't happen a lot, where like you could point out so many of these nice like these actual segments that you graphed in the slope field could all be connected to like one particular solution, like in this case where your c value was 0. And I dare say if your c value was like 1, y equals the sine of x plus 1, it would probably be, you could probably attribute all of these to that c equals 1. Huh, pretty cool. But that's slope fields, and again, let's say your dy dx differential equation was equal to, say, x plus y, then you would just literally add the coordinates, like at every coordinate, like let me go back here, you know, like let's say you were looking here, you know, if your dy dx equation was equal to x plus y, then you would do the x coordinate plus the y coordinate, because this would have literally said slope equals x plus y. And so right here, your x is 2, your y is 1, and so you would have put a slope here of 3, and you would have put a slope here of 6, because 3 plus 3 is 6. That's pretty steep, you know what I mean? But anyway, that does it for slope fields. Yay!